In this video, let's practice with Kirchhoff's voltage law. We'll look at it in a few different ways. So let's start with a fairly simple circuit which we can learn from. In this circuit, I've put in two voltage sources, and there's a mystery voltage, V alpha, we want to find, and we'll assume that Vx and Vy are known quantities. I'll give you three methods, I think. Let's start off with one that I showed you in a first video. The statement of Kirchhoff's voltage law is that voltage drops around a loop all sum up to zero. So we might identify a loop that goes this way. I think we'll also want to specify maybe this is a closed loop. That's important. Okay, so if I number the nodes, or label them, I'll call them A, B, and C. So we'll just go from A to B to C. Well, in a first method, I might consider voltage drops going from A to B, B to C, and C to A. Those have to be zero. Now we recognize that VAB is V alpha, so we can then write this as negative VBC minus VCA. And then we recognize that this is the same as VCB and VAC, right? Because of the negative sign, you can just flip the reference and the observation point around, and then you multiply by a negative sign. Okay, so basically you're reversing the direction of those measurements or those defined voltages. We can see then that VCB is negative Vy, and VAC is Vx. So V alpha is Vx minus Vy. All right, so now let's look at it using another method. And really all these methods are equivalent. Method 2 might be a shortcut for method 1. And the idea is the same. We'll follow a loop. Okay, so I've written this out. We're going to add the voltage drops in sequence around the loop. We use a plus if we encounter the plus terminal first, and a minus if we encounter the minus terminal first. What does that look like in this example? Well, let's say we go from A and B, C again. Really, it doesn't matter where we start. We could start with C. Now, as we go clockwise around this loop, we encounter the minus sign of Vx first, so we have a minus Vx. And then as we go clockwise around again, well, we encounter the plus sign of V alpha, so we put in V alpha. And then as we go this way, we encounter the plus sign of Vy, so we put in Vy. And then we equate everything to zero. And then what you see as you rearrange this is that we have V alpha is equal to Vx minus Vy. And you reference back here, you say, hey, that's the same, so that's good. The third method I'd like you to think about is finding an alternate path. And here's what I mean by that. Note that V alpha goes from A to B, and we can think of it as going across that resistor, but we can find an alternate path using variables that are known already, voltages that are known. So let me illustrate that really quick, but first let's write method 3. Okay, so as I mentioned before, we need an alternate path. So the first path was to go clockwise from A to B, and that is V alpha, but we can equivalently go from A to B, but we'll take another path where we have variables that we know, and you'll see that it's equivalent. So I'm going to go counterclockwise now, and we'll add up things as before. So going counterclockwise, right, we're going from A to B, so we'll write it as VAB, but we're going now in the alternate direction. So again, first we encounter Vx with the plus terminal, so we'll put here Vx, and then we encounter Vy with a minus terminal, so it's minus Vy. And again, you can compare this to that. It's the same. And so there we have three equivalent methods. The first one is add up the voltage drops, paying attention to which nodes you're using, and then fill in any details that you can and massage the equation so you uncover the voltage that you're after. Method 2 is completely equivalent, but perhaps a shortcut. And method 3, also equivalent, and just another way to think about it. So like, I want voltage VAB, but I follow another path from A to B with voltages that I know. Okay, I hope that helps you think about how you can use Kirchhoff's voltage law. As always, please like the video, subscribe to the channel, leave a comment, and I hope you crush your circuits in a good way.